Okay, so we're gonna put this stuff all together, and I know that again you're probably just thinking, oh my gosh, all this chemistry, but really I'm trying to keep the chemistry pretty simple, and you'll have to trust me that there's an end I'm working towards, right? So I'm not making you slog through this for no reason. So what we're going to talk about here is kind of review some of the stuff that we've already talked about, right? And really the stuff that we've been talking about is those are processes that are operating within what we call the fast carbon cycle. This is where carbon's actually moving pretty quickly throughout the Earth's system. So I've kind of taken some of the things that we've talked about already and represented them as these boxes. This is actually a figure in your text. So we've got the atmosphere up here, which contains about 850 gigatons of carbon. The land biosphere, if you remember. So I've represented some of the different reservoirs of carbon that we've been talking about, places where carbon's moving to and from, and then also the amount of carbon in that particular reservoir, in that particular kind of form, if you will. So the atmosphere, 850 gigatons. Land biosphere, so this is largely kind of the sink here is photosynthesis. Then we also talked about permafrost. So this dashed line kind of represents the difference between the continents and the ocean. Then over here we've got the mixed layer, 100 gigatons, and the deep ocean. Remember, that's where tons of carbon lives for a couple of different reasons that we're actually going to explore in the next video when we start talking about the rock cycle. Has to do with solubility. So the other thing that we had talked about was flow, right? How much carbon is moving between these different things. So I've added those numbers here. You can see 120 gigatons of carbon kind of in and out, right? That's photosynthesis and respiration, which we did to death. Here we've got carbonic acid, rainwater falling into the ocean, and then the ocean diffusing CO2 back into the atmosphere. So that's about 80 gigatons. The interface between the mixed layer and the deep ocean is about 100 gigatons per year. And the permafrost, that's actually pretty paltry, so we're going to leave it off. You know, the amount of carbon that is added to the permafrost every year is small, but because that reservoir doesn't really change, it doesn't have an out, it starts to pile up. So that's how this number gets to be so large. So what we're going to do with this is now we've got all these numbers, we've got all this chemistry, our head is spinning. But we're actually going to put it together, like I said, for a use. So how much time or how long does a typical CO2 molecule live in the atmosphere? Well, to do that, we actually just have to kind of do two things. We basically have to look at the total number of carbon, which we've got here, and then we look at the flux or the flow of carbon in and out of that reservoir. And in the case of the atmosphere, we've got 850 gigatons living there, and that has a kind of flow rate. You actually have to add these together, so we've got land biosphere fluxing at about 120, and the ocean at about 80, which is nice. It's actually an even number, at least. You know, we know that things are a little bit more complicated than that, but we're using nice even numbers to drive the point home. So that's 200 gigatons per year. And actually, if we do the math, we can then get the residence time of carbon. And so this becomes a pretty powerful equation, right? The total number versus the annual flux. If we do the division, we can actually figure out how long a molecule is going to be there, and in this case it's actually about 4.25 years. So a carbon molecule has a residence time in the atmosphere of about 4.25 years. That's pretty incredible, actually, and that's fast, right? So you can think about, you know, as we're emitting CO2, those CO2 molecules that go in the atmosphere get stripped out pretty quickly at least in this context. So we can also look at a couple of other things here. We've got the mixed layer, we've got the deep ocean. So let's go ahead and calculate residence times for those different things. Okay, I saved you all of the math, and hopefully you can see this. I'm kind of running out of room. I'm going to have to reorganize my whiteboard for the next discussion. But we already did the math here. So the atmosphere has a residence time of about 2.5 years. The mixed layer, if we do the same math, and I had actually not finished my 9 in the previous drawing. Anyways, so the mixed layer has a residence time of about 5 years. For the land biosphere, well, there's a lot of carbon in the land biosphere, and a lot of that is fairly long-term, like a tree, right? A tree is, building its carbon. So the land residence time is actually quite a bit longer, right? So about 20 years. But the big one here is the deep ocean. And the deep ocean has a lot of carbon in it, and it actually has a fairly low flux, like when compared to the volume of carbon. And so its residence time is about 400 years. So a carbon molecule that ends up in the deep ocean is going to take about 400 years to work its way essentially back into the mixed layer. And that largely has to do with ocean currents. They're not very fast. We've got downwelling and upwelling. So it takes quite a long time. And like I said, this idea of residence time, that's really where we get into the slow carbon versus fast carbon discussion, right? So all of these would generally be considered pretty fast. Well, all of them are really fast except for, deep ocean and land are a little longer. But the mixed layer in the atmosphere, that's a pretty quick turnaround. So hopefully you can understand, where these numbers come from. It's not just someone making up, how long carbon lives in the atmosphere, or even individually tracking a molecule. We look at the statistics. So what we're going to see in the next video is we're actually going to start looking at the interaction between the carbon cycle and the rock cycle, and those numbers are much larger. And that's really kind of when we switch over and start talking about the slow carbon cycle.